related rates process like just about every other word problem ever created. Well, actually, the first one, I'll take it as a typo. I wrote draw a diagram, but really draw a diagram if necessary. The idea behind drawing a diagram is for you to get a sense of the nature of the situation. If you already have a sense of it, if you already know what's going on just by reading the problem, then you probably don't need to draw a diagram. Like air being blown into a sphere. What are you going to do? Draw a ball with like wind, like a fan? I don't know. It's not necessary. All right. Determine which quantities and rates are given and which are to be found. That makes sense. 3 and 4 are the unique things. Identify the primary function to use. Often, it's a formula from geometry. That's the easy case. If you look at it and say, all right, well, sphere. I have formulas related to spheres. I have surface area, I have volume. If we're talking about a cone or a cube or something like that, you have information, you have formulas for those things. It's when they give you some weird shape and they say, okay, now water's filling this trapezoidal basin. And like, okay, wait, so it's a three-dimensional trapezoid. What's that going to be in terms of a geometry formula? You'd have to derive it yourself. Okay? But so it gets a little harder that way. But generally, not too bad, this part. The differentiating part, that's just taking the derivative. Write a related rates equation. That one seems like a very useless step. It's like, wait, isn't that the title of the lesson? Isn't that what we're supposed to be doing? Write a related rates equation. That is also known as a differential equation, an equation involving derivatives. All right, so an equation involving derivatives. All right, and that's because derivatives are rates of change. And so if you have multiple derivatives within the same equation, since an equation is a relationship between two variables, you would have a relationship between rates, related rates. All right, so that's all the term really is trying to get across. Step 6, substitute known quantities and solve for the desired rate. So that's the part where you take the numbers, you plug them in, and get an answer. You don't want to make any substitutions too early in the process, because if you do and then go to take the derivative, anytime you substitute a number in and then take the derivative, you're going to get 0 as a result. If it's a variable quantity. If it's something that's constant, its derivative should be equal to 0, and at that point it wouldn't matter if you plugged the number in or didn't. Right? So it's just a question of when is it appropriate to substitute a number in and when is it not. Right? We'll cross those bridges when we get there. All right, so that's my little notation there. Do not substitute known quantities before this last step. So the air is being blown into a sphere at a rate of 6 cubic inches per minute. All right, so we want to identify what we have here. A rate of 6 cubic inches per minute. All right, so I know that's a measure of a derivative. Per minute would be some unit of time. Cubic inches is a measure of volume. So this would be a rate of change of volume per unit of time. All right, on an instantaneous level. All right. The only time it would be an average rate of change is if they said average rate of change in the problem. All right, so if the word average is not in there, then we assume it's an instantaneous rate of change and therefore a derivative. All right, so they're giving us a dV/dt, right, rate of change of volume per unit of time. How fast is the radius changing? All right, so they're asking for a rate of change of the radius. Also per unit of time, so they're asking for dr dt when the radius is equal to 2. All right, and that's not a rate of change, that's a static value. All right, the radius is 2. It's an unchanging quantity. All right, So what I need to do is come up with an equation. I mean, I'm kind of cutting to the chase here. Step 5, write a related rates equation. I want an equation that relates all of these things together. All right? The important pieces are the dv/dt and the dr/dt. I also have an r, so if that's in my equation, that's great. If it's not a big deal either.
How is r a constant value if it says how fast does r change?
Well, it's at a particular moment in time. So we're thinking of it as a constant under a particular constraint. So the clock is ticking as the air is being pumped into the sphere, but eventually you stop the clock and stop the air at that particular moment. What's going on? So it's kind of like a freeze frame, all right, a cross section if you want. So it's not in general constant, but we're going to treat it as constant at that particular moment. All right. So a relationship. Well, we'll start with a relationship between volume and radius. For a sphere, volume is equal to what? 4/3 pi r cubed. 4/3 pi times the radius cubed. All right. Now we're going to take the derivative of this with respect to time. Right. So in terms of seconds or minutes, sorry. So I'm looking for the derivative of volume per unit of time. So we're taking the derivative implicitly here. All right. So going back to implicit differentiation, if I had something like y equals x cubed, that was easy. That was just dy dx. I'm taking the derivative of y with respect to the variable x. So for the y term, I needed my derivative, but the x term, there was nothing beyond just the power rule. But if I had something like x equals y cubed, and I was taking the derivative with respect to x, it would be 1 equals 3y squared times dy dx. All right. So then the question would be, well, now that I'm taking the derivative with respect to time, what do I do? Well, I basically have to treat each of these variables the way I treated y in implicit differentiation, because y is being differentiated with respect to x. So there was always that dy dx that got slapped on. X was being differentiated with respect to x, so we didn't have to worry about it. But here, v and r are being differentiated with respect to something other than v and r. So in each case, I have to slap on a d something dt. So on the right-hand side, I'd power rule this and get 4 pi r squared. But because I'm taking the derivative with respect to time, I would multiply it by dr dt. All right? It's really just an extension of the chain rule. If you just kind of imagine that r is some function of time, because it is, we don't know what the relationship is. We know that at a particular moment, r is going to be equal to 2, and it is changing at a particular rate, but I don't know what that function is. If we collected data, we could figure it out. You know, stop the clock after 1 second, stop the clock after 2 seconds, collect the radii, 5 seconds, 10 seconds, whatever, and then pop it in the calculator, do a regression, come up with a function. We would have an r equation in terms of time, right? Here we don't, but we have to imagine, or at least assume, that there is some r equation out there in terms of time. And so when I take the derivative, I also have to take the derivative of that inner unknown function, right? So it's 4 pi times something squared, 4/3 pi times something cubed. By the chain rule, that becomes 4 pi times that something squared times the derivative of the something, all right? So that's really all we're doing here, is just applying the implicit concept to multiple variables within the same equation. The good news is that provides us with exactly what we need, because I have a dv/dt, which is 6, and that's a positive 6. It's being blown into the sphere, so the sphere is gaining volume at a rate of 6 cubic inches per minute. r is 2 at the particular moment that we're interested in. And we're looking for dr dt. So clean it up, simplify, solve. So it's 6 over 16 pi, so 3 over 8 pi. Units are important here. So the recipe to the units are given here. dr dt, well, r is radius. Radius is measured in inches. T is time, T is measured in minutes. So inches per minute, all right? So inches per minute. Don't go decimal form. You're gonna get some funky answers here. I think actually, if I remember correctly, one answer to one problem in the packet is something like 8 over 405 pi. You're gonna look at that and be like, okay, what the hell is that? It's just an answer. I will tell you that the decimal form of this is not going to be any more meaningful to you than the fractional form, because if you can actually relate to what the rate of change of a radius would be in inches per minute, that's something special. I mean, I think you'd have to actually conduct an experiment, the balloon experiment, and actually do it somehow correctly in order to really get a sense of what this means. I mean, the idea here is if you just look at positive, negative, or 0 as the possibilities for a dr dt, positive being that the radius is increasing, negative decreasing, 0 is unchanging, that's going to give you the most information, I think. Right? The idea here is that I'm looking at 3 over 8 pi. Okay, so something really small, right? But I have inches per minute. Okay, is that really small though? I don't know. How long are we pumping air into this thing? Because I have a drip in my bathtub at home. It really pisses me off. It's that sound, the drip, constant drip. I try closing the valve, opening, closing it, greasing it, everything, and it's just that drip. It won't go away. So that's the one. It's like over and over and over again. And I know I have to take the whole thing apart, lube it all up and then put it all back together. I just don't want to do it. Right? It's a minuscule amount of water, but I mean, we've all, we've sat in the science classes, we've read the articles where the little drippy faucet amounts to gallons of water over the course of a year. So I'm looking at this saying, oh, look at a tiny little rate of change for a radius. But I don't know how long air is being pumped into this sphere. And honestly, a cubic inch is bigger than you think. So here's an inch, but then you have to cube it. So it's actually about the size, it's bigger than a die, definitely. So you're talking like something, pretty sizable. Something in this neighborhood, So I don't know. It's something that looks small might not be small. And if we're pumping this over a period of days, you're gonna have before you know it, you're gonna have a sphere that's bigger than a building. So a tiny amount, on this level, it doesn't seem like much, but it amounts to a lot. So the moral of the story there is, we can't really make a determination of what these numbers mean without any real context. And when we talk about the project, you'll get a sense of what I mean by that. So meaningful context anyway. All right, the edge of a cube is increasing at a rate. You'll like the project that'll be due this quarter, and it'll boost your grades. The edge of a cube is increasing at a rate of 2 inches per minute. All right. At the instant the edge is 3 inches, how fast is the volume increasing? All right, so another volume situation. A little easier. Volume of a cube, just take a side and cube it. All right. The edge is increasing at a rate of 2 inches per minute, so that's a ds dt. I did it a little bit backwards here. I defined my equation first with my ugly looking s for the purpose of really defining this with the appropriate variable, because you can define the edge, and people go with x, people go with e for edge, s for side. So it wasn't until we used the actual equation that we can decide that this is going to be ds dt. All right, s will be equal to 3 at the moment of interest, and we'll be looking for how fast the volume is increasing. So we're looking for a dv dt. All right, so those rates need to be related, and in order to do that, we need to take the derivative of both sides. All right, so dv dt, left-hand side, something cubed becomes 3 times that something squared times the derivative of the something, which would be ds dt. It's only after you take your derivative that you start plugging and chugging away, right? Unless you know something is always constant. All right? There's, I think it might be on the next page, there's a ladder question, like the ladder sliding down the wall. In those questions, the ladder, unless they say otherwise, the ladder's length is not going to be changing. So you could assume that's constant, right? And that might factor into the problem in some way. Right? But here, I can just plug away at this point. We've taken the derivative. We did all the hard work. So the s is 3, and we're looking for dv dt. So it's already solved for the thing that we're looking for, which is great. So dv dt is going to be 3 times 3 squared times 2, which is what, 54? All right, so it's a measure of volume, which is a cube of the linear units used. So inches cubed, because it's volume, per, in this case, minute. So in number 3, a point moves along a curve y equals x minus 3 squared, such that its x-coordinate is increasing at 4 units per second. At the moment x is equal to 1, how fast is the y-coordinate changing? All right, so it's basically giving us a nice little recipe here. They're telling us that the x-coordinate is changing or increasing at 4 units per second. So that's the dx dt. And it's increasing, so we just keep that in mind. Because if it's decreasing, then we slap a negative onto that, whatever that number is. All right. They're telling us that x is equal to 1. So we can jump right into the derivative part of this. All right, so y is equal to x minus 3 squared, dy dt. So it's definitely chain rule in its current form, but it's like baby chain rule, right? Because the inner function has a derivative equal to 1. So if over the break you forgot everything about chain rule, you'd probably get away with it on this one because the inner function is just a 1. But then because it's a related rate situation, I have to take the derivative with respect to t. So the derivative of this is 1, but multiplied by dx dt. And it's easy enough to distribute out also, and then just go with the power rule. If you did that, you get 2x minus 6 when you take the derivative. Well, 2x minus 6 times dx dt. All right, so we could plug and chug now. We're looking for dy dt. So it's going to be 2 times 1 minus 3 times 4. So is that negative 16? And so the units for x, there's no reason to think the units for y would be any different, were units per second. Shouldn't even be awake right now. Got another hour and a half before I should be waking up. At the moment x equals 1, how fast is the point's distance from the origin changing? That's a little bit more interesting. This is obviously a parabola, but part B is not really asking about movement along the parabola directly. I mean, indirectly, definitely. Let me just do a quick sketcheroo here. My y-intercept would be 9, right? That's like something like this. At the moment x equals 1, and 1 corresponds to 4, right? It's talking about the distance from the origin. All right, so you could use distance formula. You could also use Pythagorean Theorem. All right, if we use Pythagorean Theorem, I think the work is a little bit easier. So make a triangle. I mean, any distance can be decomposed into horizontal and vertical vectors. So there's no reason not to. I mean, if you like the distance formula, that's fine. It's just, it's a radical containing two squared binomials. It's going to be chain rule within chain rule. So it's going to be doable. You'll get the right answer. I mean, you're not going to fit it in that space, but that's par for the course in this class, I guess. So yeah, it's just going to be a lot more work, I think. I mean, very doable, but probably not what you want to do. All right. So we have an x, we have a y, and we have a d. That's going to look weird. I'm going to call it r. Because when I take the derivative, I'm going to have like d something. It's just, I'm not even going to like saying it, so make it a dr. And generally, the hypotenuses are abbreviated using r's, just in general, whenever you're dealing with triangles, for some reason. The reason is that any line segment could be thought of as the radius of a corresponding circle, which is really kind of strange to think about. But in Calc 3, so that's 2 levels. Well, if you test out of this one, yeah, so it would be your second semester in college if you were to go a pure math route. You'll learn about how to parameterize. It's pretty cool, but really what happens is you'll have some kind of curve, and instead of thinking about it in terms of x and y values, you'll think about it in terms of radii. So every little distance along that curve, like this little guy here, you'll say, all right, that's a good little curve. I can find out a little segment there, or I can think of that as a tiny little arc length of a corresponding circle that would have its own radii, and define the circle, and then work off of that circle calculus. The reason behind that is, whether you like it or not, trigonometric calculus is a whole lot easier than non-trigonometric. The idea behind that, and it doesn't seem like that's true. It's like he's lying. He's clearly lying to us. Like the algebraic stuff only goes so far. You know, there's only so many things you could define with simple polynomials, radicals, rational expressions, things like that. Eventually, the algebraic expressions get so cumbersome that you need to move away from them because they're not things that you can take the derivative or antiderivative of. Okay, so we end up needing trigonometry. But the fortunate thing about trig is if I were to ask you right now what the antiderivative is of cosine, you can tell me that. But if I asked you what the antiderivative is of 1 over 1 minus x squared, it's going to take you a few more minutes. Right? So, by the way, what is the antiderivative of cosine? Yeah, sine. Yeah, because if antiderivative is the opposite of derivative, you're just thinking about the thing that gave you a derivative of cosine, and that would be sine. Right? So, the trig stuff is really where we want to be. Anyway, that's the justification for calling it R. It seemed like I'm answering a question that you didn't ask, probably, didn't necessarily care about. Might fall in the category of fun fact of the day, but at some point down the line, it'll be important. So x squared plus y squared equals r squared. We could, if we wanted to, take the square root and then take the derivative, because in fact we are looking for dr dt. You know, saying how fast is the point's distance from the origin changing. So I am looking for dr dt. If I solve for r, I'll directly be able to get that. The only issue is I'm creating the thing that I was trying to avoid with the distance formula, the radical containing a mess. All right, so let's take the derivative of this as is with respect to time. So 2x times dx dt plus 2y times dy dt equals 2r times dr dt. All right, none of these quantities are constant because depending on where I place that point along the curve, I'll get a different triangle with different legs, different hypotenuse. Right? Every length is going to be completely different. Right? So everything is changing. You know, if you can actually visualize this, I'll show you on GeoGebra tomorrow. It's really kind of cool. But if you slide the point along the curve, the triangle, corresponding triangle, is going to change accordingly. Right? So there's no reason to think that anything's going to zero out here. There are situations, like in the very next problem, where part of it will zero out because the ladder's length is not going to change. Right here, the hypotenuse will change. One good thing is that the 2's are going to cancel out across the board. Now, it's a little something. All right, we're still talking about the x value of 1, which corresponds to a y value of 4. We figured out what dy dt was at that particular moment. The preamble said that we were looking at a dx dt of 4, so we have pretty much everything we need, or almost everything. So we're looking at 1 times 4 plus 4 times negative 16, that's what we got from part A, equals the r, which is not yet known, times dr dt. All right, just kind of off on the side. We have a leg of 1, another leg of 4, and I'm looking for r. Pythagorean Theorem. It's the sum of the squares, right? So square root of 17. All right, so I'm taking the 4, subtracting from it was 64, so negative 60. Am I right there? 4 minus 64, negative 60, over rad 17. So dr dt and these are linear units. We're not talking about area, volume, or anything like that. So the linear units are the same linear units that were used for x and y. So units per second. All right. So again, this is what I was talking about before. You look at negative 60 over radical 17. You're like, I don't know what that means. Is that a lot? Is that a little? I don't even look at that. I just look at the negative sign. That's telling me that at this instant, the length of the hypotenuse is decreasing. So it's getting smaller. So if you actually take two fingers and trace it along the curve, you can feel that happening, right? So as you slide along the curve, you can feel your fingers getting closer to one another until you get to a particular moment where those fingers start getting further and further apart. There is some moment over here where your dr dt would become 0 and then transition from 0 to positive, right? So that's where it starts increasing. So down the line, we'll start learning about how we can figure out that kind of thing. But you know, there's definitely some meaningful applications to it. So what I'll ask you to do for homework would be just the next two problems. I mean, I suppose you could do the next three, but I wanted to talk you through the last one because there's some funk involved in it.